Okay. Vapor pressure of liquid solution. Let us consider a binary solution of two volatile liquids A and B. Vapor pressure of both vapor pressure of both A and B in pure state. Vapor pressure of both A and B in pure state are PA naught and PB naught respectively. So vapor pressure of both A and B. Basically here vapor pressure of both A and B in pure state. This is pure state. Okay, it's not mixed both A and B. No, means it means that vapor pressure of both A and B in pure state means purely. If it is only A state are P naught and P naught respectively. Chi A is mole fraction of A here. Chi B is mole fraction of B here. As the components are equivolatile, so an equilibrium exists between liquid. Okay, it means that as components are volatile, so basically it means that as these components are volatile, so an equilibrium exists between liquid phase as the components are equivolatile, as the components A and B are volatile. That's why equilibrium exists between liquid and phase and vapor phase. So equilibrium exists between liquid phase and vapor phase. Okay. After this, we have, let us take chi A. Let chi A and chi B are the mole fraction of A and B in the solution liquid. Okay. So let chi A and chi B. Let chi A and chi B are the mole fraction of A and B in the solution. So here chi A and chi B are mole fraction of it in solution. Okay. And PA and PB are the partial pressure of A and B in the solution. The partial pressure is A and B, and the mole fraction of A and B are chi and chi B. There is a relationship between partial pressure. Partial pressure means in the solution. Okay, there is a relationship between partial pressure. There is a relationship between partial pressure and mole fraction of the component, which is known as Raoult's law, special case of Henry's law. Special case of which law? Special case of Henry's law. Okay, Raoult's law. It's important. Okay, and one more thing here is that chi and chi B mole fraction of A and B. Okay, P and PB base subset of A and B. P naught partial C. PA naught is basically means that pressure of A in pure state, and PB naught means the pressure of A in pure state. Pi A means mole fraction of A in vapor phase. So this vapor phase, there is, you just see the equilibrium sign. So Y are mole fraction of A in vapor phase, Y is mole fraction of B in vapor phase. Okay, and one more thing here is, as the components are volatile, as this component is volatile means what? It will easily vaporize if you just boil it a little bit. So as components are volatile, so an equilibrium exists between liquid phase and vapor phase. Okay, so now let's move to Raoult's law, special case of Henry's law. What is Henry's law? Henry's law is basically pressure is equal to kh into chi, where kh is Henry's law constant. Okay, so after this, the partial pressure of a component in the solution is directly proportional to the mole fraction of the component. Okay, it basically tells you that the partial pressure of a component in the very solution. Okay, so in solution, the partial pressure of the component will provide proportional to mole fraction of the component. So this thing, and P naught is the pressure of A at pure form. I think it's written here for component A. Y equal mx plus c. Good formula. So y is this, x is this, plus c, this is m. C is 0, y equal to mx. For y equal to mx plus c, c equal to 0. So if a graph is plotted in between chi a and chi a as x axis and p as y axis, nature of graph is a straight line with a maximum value of p a naught. Maximum value of p a naught. Okay. So after this, y equal to mx. So y equal to mx plus c equal to 0. So if a graph is plotted in between x a as x axis and p as y axis, nature of the graph is straight line with maximum value of p naught. Okay. So this is so why p naught is the maximum value? Because you will see x a could maximum go to 1. So we are basically doing what? Y by x, which is PA by x. Okay, so if x is equal to 1, means what is xa? Xa means Na by Na plus Nb. AB is solvent. So if Na is equal to Na plus Nb, means Na becomes Na plus Nb. Basically, if Na takes up the whole solution. Okay, Na takes up the whole solution so that Nb becomes 0. So this becomes 1. So if it becomes 1, then we will say that in the solution only A is there. So this would be the pure pressure of A, because you understand, right? Because Na plus Nb was there, but now we have taken Nb as 0, and we have done this thing as 1, Ia as 1. How it would be 1? If both numerator and numerator are same, so if we can do 0, we increased Na such that Nb is tends to 0. So okay, next let's move on. For component of B, Pb is proportional to chi b, and it's Pb naught. So if graph is plotted between chi b and Pb, nature of the graph is a straight line. Okay, so if a graph is plotted between Pb and chi b, nature of the graph is a straight line having maximum value of Pb naught. Okay, here we are again doing the same thing. We are taking chi b as 1. So how it would be 1? It would be 1 because when Nb plus Na plus Nb is equal to 1, means basically Nb becomes 0 and Nb remains there only. So how when it doesn't become 1? When the solution has only B, so this becomes pure pressure, partial pressure of pure B. Then when we will decrease this thing from 1 to 0, when we will decrease this string chi b from 1 to 0, this basically means that Nb by Nb is not there, and some Na is also there, means Na is increasing. So if Na is increasing, this thing is increasing, so this is decreasing, and if you just increase it so much that only Na is present in the solution, okay, if Na is present in the solution, then the thing is that this becomes, let's say, infinity, then 1 by infinity is 0. Or I can say that if only Na exists in the solution, means if Nb becomes 0, because Na is only existing in solution, right? Basically Nb is becoming 0, so only Na is existing in the solution. So if Na is existing in the solution only, then Nb would be 0. Why Nb would be 0? Because there is no B in the solution. Number of moles of B is 0 because there is no number of moles of B in the solution. So 0, it would be 0. Okay, so that's it. Okay, now let's move on to the next. According to Dalton's law of partial pressure, P total is equal to Pa plus Pb. And we know that from Raoult's law, Pa naught chi A plus Pb naught chi B. Pt is equal to Pa naught chi A, Pb naught 1 minus chi A. And we have Pt is equal to Pa naught, or you can also write Pa naught 1 minus chi B plus Pb naught chi B. So if we just plot the graph of the Raoult's law or Dalton's law of partial pressure, we will see that this is Pa, this is pressure, this is your chi. So if we just decrease it chi from 0 to 1, then chi A from 0 to 1, chi B would decrease from 1 to 0, increase from 0 to 1, chi would decrease in 1 to 0, because only when chi A is 1, then that means that only A is existing in solution and no B is there, so that's why it's 0. Okay, I've told you just now only. So basically 0 to 1, this is chi A. So we've done this graph here, chi A 0 to 1. So just plot the same thing, and chi B is from 1 to 0. We've done again here, chi B is 1 to 0, and this again. So we are doing this again, so this thing, and you just see this thing is chi b, and this thing is this thing is what? Chi a. This thing is what? Chi b. Understood? This thing is what? This thing goes up. This thing is basically means this is A's graph, not chi a. This is B's. Okay. So now after this, you just plot PT, total pressure, which is given by this formula. So first of all, at this point PV naught is fully there. So it would be PV naught into chi b is here 1. So PV naught would be there. And at this point, PA naught is existing, and chi a is 1 and chi b, and your chi a is 1 again. So 1 minus 1 is 0. Okay, so this thing doesn't exist, only P naught chi a naught, P a naught chi a exists, and chi a is 1, so P naught would be the total pressure here. So, and this thing, how we would get this thing? So basically, if you just the negative value of P total must lie in between the values of P a naught and chi PV naught. Basically, it's telling you that the value of P total must lie in between the values of P a naught and PV naught. Okay. Values of P total must lie in between values of P a naught and PV naught. The higher value of PT nearer to P a naught indicates in the solution the amount of A is high and B is less. Okay, so basically it means that if the higher value of PT, nearer to the P a naught, okay, indicates that in solution amount of A is high and B is less. Basically, it's telling you that if you will just increase chi a, then your this thing is increasing, because chi a is solute. Okay, so that means that surely a lower value of PT, that is nearer to PV naught, indicates solution amount of B is high. Sorry, lower value of PT nearer to PV naught indicates the solution of amount of B is high and A is less. Okay, so what does it mean? It means that a higher value of PT, that is nearer to PA naught. It's saying that a higher value of PT that is nearer to PA naught indicates the solution amount of A is high and B is less. Similarly, a lower value of PT nearer to PB naught indicates the solution value of amount of B is high and A is less. Solution amount of B is high and again, a high value of PT that is nearer to PA naught indicates the solution amount of A is high and B is less. It is not telling that A is solvent or solute. It's telling that the solution amount of A is high and B is less. Okay, solution amount of A is what? Solution amount of A is high. Okay, one more thing is why the graph is only like this, because you will see that PA naught value is higher than PB naught value. That's why the graph is like this. Okay, now another thing is that if you will just move this point, I'm explaining this point. So if you will just move downer and move nearer to, then the lower value of PT that is nearer to PB naught indicates the solution amount of B is high and B is less. Okay, so if you move, if you just decrease PB, not PT, and if you see moving towards PB naught, that means that chi B is increasing. It is increasing to 1, and chi B is increasing to 1. That's why 1 minus chi B is increasing. So which means chi is decreasing. So at that point, chi B means B is more and A is less, because NB by NA plus NB. NA is decreasing, so it is increasing, NB is increasing, so it is also increasing. Okay, and your it's not like that. Basically, it means that chi B is increasing I'm telling you like this. See, chi b is increasing 0 to 1 and this is decreasing 1 to 0. Okay. Similarly, if you just increase pt value and move to pa naught, then basically chi a is increasing 0 to 1 and chi b is increasing 1 to 0. And one more thing is why we are increasing pt to get pa naught, because pa naught value is more and p naught value is less. Means it's like this: 5 into 1 is more, but 2 into 1 is less. That's why it depends basically on p naught and pb naught. Okay. And if you just add up 5 into 0, nothing would be there. And if you just, let's say 2 into 2, 4, and let's say 5 into 10, 10 plus 4, 14. Okay, no, it can't be 2, sorry. If you just take its half, this is as half, no, not half. Let's take it as 3 by 4, 3 by 4. Let's take it as, don't take anything, this is the thing. Okay, now let's move on to next portion. Next portion is Korn-Waldorf rule. Okay, Korn-Waldorf's rule, applying Dalton's law of partial pressure in the vapor phase, Pa is equal to chi a into Pt. Okay, so basically Pa is equal to, now let's move on to the Korn-Waldorf's rule, applying Dalton's law of partial pressure in the vapor phase, Pa is equal to chi a into Pt. Now chi a, chi b is in the liquid phase and y b in the vapor phase. For compound A, Pa is equal to y into Pt. Okay. Now for vapor phase, Ya is equal to Pa by P total, which gives us P naught by P naught chi a by P naught chi b, chi a plus P naught chi b. Okay. So Ya would be equal to Pa by B total, which is Pa naught by chi a by Pa naught plus P naught chi a plus P naught chi b. For component B, Pb is equal to Yb into Pt, Yb is equal to Pb by Pt, Pp is Pb naught by chi b, and Pt is P naught chi a plus P naught chi b. So this whole thing is for vapor phase. So this whole thing is for vapor phase, and chi is partial pressure of, chi is partial, chi is number of moles of A in vapor by total number of moles of A and B in vapor. And similarly V naught chi B. Okay, and chi B is the number of moles of B but in vapor phase. Okay, so chi B means that only, means it's in vapor phase. Okay, partial fraction of A in vapor phase, partial fraction of B in vapor phase, partial fraction of B in vapor phase. Okay, now let's read some questions. Next is ideal and non-ideal solution. Ideal solution which satisfy this thing, non-ideal solution which doesn't satisfy this thing. So there's two cases. Case 1, Pt is greater than positive deviation and smaller than negative deviation. So basically we have done this graph, Pb naught, Pa naught. Okay, Pb naught, Pa naught. Okay, so if this thing is ideal solution, okay, we have done this. Then we have this one on a non-ideal solution. This thing would go up by positive deviation, and if it will go down, this is for negative deviation. Means basically, which one is going down? So okay, so this thing. Okay, so graph is not there. Means basically this thing, if it goes up, this thing would be positive deviation. Everything goes up, and if everything goes down, then it would be negative deviation. Okay. Now we've done this. Now let's move up. Okay, so this thing, don't ignore this. This is not correct graph. Okay. Now ideal solution, for ideal solution, for such solution, P total is this thing. In this type of solution, the solution is 0. Ideal solution, relative solution is also 0. The solution is 0. You have to remember the solution is 0. Relative solution is also 0. Okay. So basically, for ideal solution, Del solution is 0, del solution is also 0. Now amount of components leaving the amount of component leave the solution surface is total evaporation and is proportional to rate of tendency of evaporation. It basically means that total vapor pressure is proportional to rate / tendency of evaporation. Rate of evaporation is amount of components leaving the solution surface. Solution surface means this is solution. If this is solution, the surface, the amount of components. Okay, the amount, how much, the amount of components. So there are two components, solute, solvent. The amount of components leaving, amount of components. So let's say 5 grams of solute and 5 grams of 10 grams of solvent have left. So the amount of components leaving the solution surface, okay, is proportional to rate of evaporation, and rate of evaporation is proportional to vapor pressure. So if more the solute, more the solvent will evaporate, then total vapor pressure will be more, because indeed vapor pressure is basically the pressure of gas. So if more the pressure, more the evaporation, more the exertion of gas, more the exertion of gas, more the pressure of the vapor pressure, more vapor pressure. Okay, amount of components leaving the solution surface in inversely proportional. Now amount of components leaving the solution surface is inversely proportional to the intermolecular force of attraction among the components. So basically, I have told you, if this is a solution surface and the 5 grams of solute and 5 grams of solvent left, so that is amount, is inversely proportional to intermolecular force of attraction among the components. So intermolecular force among the components. So basically, if the intermolecular force between the solute and solvent is more, it would be difficult to you. Let's say the mass of solute is 1 gram. Let's say mass of one atom of solute is 0.005 gram, and this thing also 0.005 gram. So if you add it up, it would be more mass. So to remove it would be difficult. We need more heat to evaporate it. But if it just solute gas evaporates, then it would be easier. If P observed is equal to P calculated, then there must not be any changes in intermolecular forces. It is cohesive AB, BB, and intermolecular force adhesive AB, BB. That is, but basically telling us that if P observed means if the P observed, what does it mean? Means the observed pressure if is equal to calculated pressure, then must not be any change in the intermolecular forces. That is, cohesive must be same. Intermolecular force adhesive must also be. AB is adhesive, AA is cohesive, same molecular force is cohesive, different molecular forces is adhesive. So telling that if P calculated observed is same, means the P pressure observed, partial pressure we observed in the vapor phase is, if the both are same calculated, then there must not be any change in cohesive. So basically if P observed is equal to P calculated, then there must not be any change in the intermolecular forces cohesive AB, AA, BB, and intermolecular adhesive AB. So EA will be equal to EBB is equal to EAB. This is for ideal. Thermodynamic parameters like del G and del S should be less than and greater than. Del G must be less than 0, del S must be greater than 0, because the process is spontaneous. Okay. What is the solution of benzene and toluene? Example is benzene and toluene and n-heptane and n-hexane. No solution is perfectly ideal. Non-ideal solution. Okay. A non-ideal solution, negative deviations in vapor pressure proportional to ability of the molecule to leave the liquid surface. Now, if since vapor pressure is proportional to ability of the molecule to leave the liquid surface, so negative deviation will arise when intermolecular force of attraction between the solute and solvent is more than the cohesive intermolecular attraction. So let's repeat it again. Non-ideal solution, negative deviation. Since vapor pressure is proportional to the ability of molecule to leave the liquid surface, so negative deviation will arise when intermolecular force of attraction between solute and solvent is more than, so basically intermolecular force of attraction between solvent and solute is more than the cohesive intermolecular attraction in solute and solvent, hence EAA EBB would be less than this thing. Okay, so now let's move on. So now different thermodynamics parameters. Okay, basically different thermodynamic parameters during negative deviation. Del G solution must be less than 0, del S must be greater than 0. So this is for negative deviation. For positive deviation, this is what the opposite, quite opposite. Del G is less than 0, del S greater than 0. So here it's quite same, del G less than, del S greater than 0. So now del H solution must be less than 0, so it would be negative. Del V solution less than 0, it's negative. Okay, so after this let's move on to next topic. Examples of such solutions are chloroform plus benzene, CH3 plus benzene. Then we have the electron deficient hydrogen in chloroform accept electron from pi electron cloud of benzene. Okay, now acetone and aniline. Acetone plus aniline. Acetone plus aniline is CH5NH2 and CH3 C double bond O CH3. Aniline we have just studied in aniline chapter. Acetone plus aniline, then this is hydrogen bonding, and again hydrogen bonding, chloroform plus acetone. Chloroform is CH3Cl. Okay, then we have acetone is C double bond O CH3 C double bond O CH3. So hydrogen bond will be formed with H double bond O oxygen and carbon, I think. Okay, now next here is H2O plus formic acid, HF plus ROH. Okay, next is HCl plus H2O dipole interaction, HNO2 plus H2O has double bond interaction. There are examples of negative deviation. Okay, CHNO plus and chloroform plus diethyl ether, Ca2H5OHO C2H5, and hydrogen bonding will be formed when diethyl ether. This is diethyl ether and chloroform CHCl3, so H and O forms hydrogen bond. Now we have next is positive deviation. Okay, positive deviation. Now basically del G solution and del S solution remains same for positive, negative and neutral ideal solution. Positive deviation, negative deviation and ideal solution. But del V solution becomes positive for ideal, for positive deviation, and del H also becomes positive for positive deviation, and if it was negative deviation it should be less than 0, del V and del H, and for ideal it must be 0. Okay, so now let's move on to the next thing, which is uh, okay, so now let's move on to the next thing, which is this thing is done. Okay, examples of such solution are examples: ethyl alcohol C2H5OH plus H2O due to bulky group of due to the number of hydrogen one decreases. It is telling due to bulky group of C2H5OH plus H2O hydrogen bond decreases. Now acetone plus CH2 due to CH2 polarity lost. It's basically opposite of negative deviation, quite the opposite. See, dipole interaction, it is due to CH2 polarity lost. Then we have hydrogen bonding lost. Hydrogen bonding here, and here it is due to bulky group number of hydrogen bond decreases. Now H1 plus benzene due to bulky group phenyl group polarity lost polarity. Then again we have colligative properties. This is a graph for it. Positive. We have done this. Okay. Now let's move to colligative properties. These are the properties of a solution which depends upon the relative number of solute particles or number of solute particles per unit volume.